So the part that we have here is that I asked you to work through was through these two experiments where you looked at the two different experiments where work was being done by the hands on the blocks, and whether that was, or so in experiment one, it asked you to consider a system of the blocks plus the spring, and in experiment two, it asked you to consider just the blocks. So in both cases, the work was the same. It was positive because the blocks are moving in the respective directions that the hands are pushing. So in experiment one, that external work from the hands goes into potential energy of the spring, and in experiment two, it just goes into kinetic energy of the blocks. So then, there was another system with a spring that wasn't as stiff, so it wasn't enough, or not all of the energy went into potential energy of the spring. Some of it still would have been in kinetic energy because the spring was not as stiff, so it didn't have as much potential energy. Okay, so I want to start here. So this is looking at the blocks as a system. Sorry, whether you want to define your system as just the block or the block plus the spring. So the thing that I want to point out here is that what you choose to look at will, as your system, will define what kind of energy, what kinds of external work you may have. So if you define your system as just the block, then you're going to have, acting on the system, you'll have the normal force and gravity, but those, because the block is not moving in the vertical direction, those don't do any work. But you'll have a work or an external force from the spring on the block. But if you define your system as the spring and block together, then the only force, you'd still have the normal force and gravity, but then you'd also have a force from the wall on the spring. But because the wall doesn't move, it doesn't do any work on the spring. So if you define the whole system as spring plus block, then you don't have to consider work. You would just be talking about all of those, all of the energy is internal to the system, right? So it would switch from, when it's initially stretched, you'd have some potential energy in the system because the string is stretched, and then that would all become kinetic energy. But there's no external work on the system because you're ignoring friction, right? So in the case of just the block, the work done externally would be by the spring. So the spring is pulling it in the direction that it's actually moving. That would be a positive work. But if you look at the spring block system, there is no external work, and you do it all in terms of energy. Okay, so as I've mentioned before, the choice is always going to be, when you're solving a problem, the choice is generally up to you. But I find that most people prefer to define the system as broadly as possible and only think about work when they have to. So, okay, so with that kind of in mind, I'm going to share a different screen now. All right, so here we have a screen that has a example problem that I'll be able to write out here. Unfortunately, can't really, you'll be able to see like all of my tools and stuff. There's not really a presentation mode. Okay, so we can read here let me mute my notifications. Okay. So the problem here we have is a bungee jumping problem, and you can see the picture there. So we have a person with a mass of 100 kilograms. They want to go bungee jumping from the New River Gorge Bridge in West Virginia. This is a place I've been. I did not go bungee jumping. I was there to go whitewater rafting. But this also, if you ever find the West Virginia State Quarter, this is the bridge and the gorge that's on there. It's a pretty tall bridge, quite beautiful scenery. So the bridge, I looked this up, it's 276 meters above the water, above the river, and kind of a common length for a bungee cord is 40 meters. So the question that we have here is, what would be the minimum spring constant for the bungee cord that would be needed for the person to do the jump safely? Right. So whenever we have an energy problem, we have to pick two well-defined points in space where we're going to look at the energy at one and compare it to the energy in the other. So what would those 2 points be if you're trying to find, you're just barely making it safe? So I'll give you a second to think there. What would be the starting point and what would be the ending point if you're just going to barely be safe enough to do this bungee jump? Okay, so what we're going to want to look at our point one is where the person is first jumping, right from there. And then point two, well, if I'm just going to barely have a successful bungee jump, that means that the person is going to make it all the way down, basically just till they reach the level of the water before they turn around. So point two is going to be down at the water, right? So we want to write our energy at each of those points. So what I generally do is say, okay, so I label this E1 for the energy at point one. What types of energy could possibly be involved in this problem, right? So I start as broadly as possible. So I might have some potential energy due to gravity. So PE sub G. I might have some potential energy from the bungee cord, which is going to be a spring potential energy. And I might have some kinetic energy. All right, so that's at the top. And then I want to look at all of these and see, well, okay, are any of these zero? So I can get rid of them right away. Okay, so with potential energy due to gravity, we always have to define where our height is going to be zero, right? So that's up to you, but here we have a nice convenient definition to call the height equal to zero when the person would be just about to touch the water, right? So then we have the height of 276 meters up at the top, right? So we know that there's going to be some potential energy due to gravity, but the spring is not, or the bungee cord is not stretched at first, right? It's not going to stretch until the person has jumped and gone down at least 40 meters, because that's the length of the bungee cord. So I can cross out the spring potential energy, right? So and say that's zero. And then for the kinetic energy, well, you're basically going to just step off, right? So you basically have a velocity of zero when you first start. And so, so that is also going to be zero, right? So when we start, we just have the potential energy due to gravity. So I can copy that down, and we remember the formula for the potential energy due to gravity. It's the mass of the person times the acceleration due to gravity, g, and then times the height, h. Right, so we start with just potential energy due to gravity. All right, so I'll give you a minute to work on your own. Try writing out what types of energy would be present when the person is at point 2. Right, so you can include all of them, all of the 3 types, but then decide which of those would be equal to 0. All right, so I'll just write out all those types. Okay, so well, when you're at point 2, you're at the point where the height is equal to 0, so the potential energy due to gravity would be mg times 0, so that term is going to be 0. The potential energy due to the spring from the bungee cord, oops, undo. The spring is stretched there, so we are going to have that. And then we've got the kinetic energy. So if you're turning around, right, if you still have some kinetic energy when you reach the river, you're bungee jumping wrong, right? That's going to be bad news. So we want that to be 0. So that means that energy 2, E2, is just equal to the potential energy from the spring, which is going to be 1/2 k, oops, kx squared. Okay, so I'll kind of box those in if I can, maybe not. So we've got E1 and E2. So those are our expressions. Now, when we go to actually figure this out, we've got 2 different distances involved, right? We've got the height, but then we've also got x, which is how much the spring is stretched at point 2. So we'll have to make sure and probably make in our drawing an indication of where x fits in. But before we do that, the other thing that we have to do whenever we do an energy problem is we say, okay, is the energy at point 1 and point 2 the same, or is it not? Right. So that the way that we figure that out is that we say that the external work on the system, that's equal to the change in total energy. Right. So that would be the change in energy is E2 minus E1. So if we're defining, if we've defined a potential energy due to gravity, that means that we're including not just the bungee jumper in the problem, we're including the Earth, right? So our system includes the bungee jumper and the Earth. And if we have a potential energy from the spring, that means our spring, or our bungee cord in this case, is part of the system. And so our system is the person, the spring, and the Earth. So now we need to say, well, are there any forces that we're considering that would be external to that system that would change the energy? Now, in reality, if you're jumping off of a bridge this tall and falling for 40 meters before your bungee cord even starts stretching, yeah, you're going to be there's going to be some air resistance, but we're going to ignore that for this class. So if we ignore air resistance, there's no other external forces on this system. Everything is internal to the system. So our external work then is 0. So that means our change in energy is 0, or another way of saying that is that E2 is equal to E1. Right, so that means that E2 equals E1. So we've got mgh is equal to 1/2 kx squared. All right, so now we need to figure out how x fits into this this picture. So let me zoom in on that picture a little bit. So we know that the person's going to fall for 40 meters. The length of the bungee cord, so I'll write that as L equals 40 meters. Before the spring starts stretching. And so then this distance from where the spring starts stretching to the water, that distance is going to be equal to x, or that's what we're calling x. Right, so L is, got a laser pointer. So L is this distance from here to here. And then x is this distance the rest of the way to the water. So that what that tells me is that x plus L is going to be equal to the height of the bridge. Right, so just by doing the quick math, the total height of the bridge is 276. The length of the bungee cord is 40 meters, so that means that the stretch of the bungee cord is going to be 236 meters. Right. Now to work in terms of variables here, I'll say that x is equal to the height of the bridge minus the length of the bungee cord. Okay, so then I can write mgh is equal to 1/2 k h minus L squared. So now in this equation, I have, well, what am I trying to figure out? If we go back to the problem statement, it says, what is the minimum spring constant that's needed for the person to do the jump safely? Right, minimum spring constant. So we're trying to find the value of k that would let the person go all the way to the water, which is how we've set up our problem. So we're trying to solve this equation algebraically for k. All right, so I'm gonna change color to do my algebra here. Right, so I want to get this k by itself. So that means first I'll divide both sides by h minus L quantity squared. H minus L quantity squared. Right, so that'll make this equation then becomes, I've got mgh divided by h minus L quantity squared, and that's equal to 1/2 k. And that's a lowercase k, by the way, for spring constant. I know my handwriting's not great, especially using my stylus on the phone screen. And then we need to get rid of the 1/2, so we'll multiply both sides by 2. So altogether, that gives me K is equal to mgh over, oh, sorry, I forgot the 2. So 2 times mgh divided by h minus L, quantity squared. So plugging in values, I've got 2 times 100 kilograms times the initial height, which is 276 meters. And then divided by h minus L, so 276 meters minus 40 meters squared. All right, so we can plug that into a calculator. So 2 times 100 times 276 divided by 276 minus 40 squared. So you got something in the chat here. Ah, thank you. I forgot to multiply by G. So let's see. So I've got 9.8 times that. Thank you for those who caught that. So times 9.8 in the numerator. Right, okay, so I've got 2 times 100 kilograms times 276 meters times 9.8 meters per second squared. And then all divided by, you know, I've still got it written as 276 minus 40, but that's really 236, right? You could do that in first. And so that ends up giving me a spring constant of 9.7 newtons per meter, which is not a very stiff spring, but you know, you're allowing it to stretch 236 meters with somebody's body weight. So see, screen sharing went away because I moved away from that window. There we go. So that value of K then is 9.7 newtons per meter. Which is, as I said, not that stiff of a spring. Right. Any questions about this example? Guess I can't really see anything because nobody's doing video, which is fine. Okay, so I did this problem with using conservation of energy, right? Defining my system as broadly as possible, but you could have defined your system any other way, right? You could have just said, well, let me take the bungee jumper as my system and then treat gravity as an external work and treat the spring as an external work, right? Gravity doing positive work because the person's moving down and gravity pulls down. The spring doing negative work because the person moves down, but the spring pulls up, right? And then just say, well, we start with 0 kinetic energy and end with 0 kinetic energy, right? So you're just looking for a total work of 0, right? To where the spring's work cancels out the gravity's work. you'd end up with the same equation in the end in terms of trying to solve for the spring constant. You know, just something I kind of want to point out here, with all these problems, generally we're trying to use either work or energy to try and calculate something else, right? Like I don't really care about, you know, what's the value of the potential energy of the spring when it's fully stretched, right? In terms of, you know, a potential energy measured in joules. You could ask that, we could calculate that, but what's really interesting is using energy or work to try and figure out something about one of our kinematic variables, you know, what we've been interested in this whole semester, right? Or something to do with the spring. Let's see, get the chat. Okay, so why are E2 and E1 equal is the question. Will they always be? No, they won't always be. So they're equal in this problem because the external work is 0, right? So I think this sort of procedure of writing down, you know, define your system, then you write down your energy at point of the system at point 1, the energy of the system at point 2, and then say, okay, the external work is equal to the difference between those, or the change in energy. Then say, okay, was there anything that was left out, right? So were there any external forces that I can't include in my system? If there is, then the energy is not going to be the same, right? But in this case, we've taken care of everything, right? There's no, we're ignoring any effects of air resistance because that's too complicated for this class. So we're just assuming that it is negligible. So in this case, E2 and E1 are going to have the same value. But that leads nicely into the next example, which is blurry at this point. Hopefully it will. There we go. Okay, so here we have a child goes sledding down an icy hill before reaching level ground 15 meters below. They slide into an area of grass which has a coefficient of friction of 0.20. How far do they slide before coming to a stop? Right, so as soon as you see friction in a problem, or if you have like a person pushing or pulling on something, you know that you're going to have to include external work in that problem. So let me draw a little sketch of the problem here. So, okay, that's a very extreme sledding hill, but that's okay. And we can add in our grass. It's probably brown and dead because it's wintertime if you're going sledding. So, and then we have the child in the sled, starts up here. And then comes to a rest somewhere down here. Okay, so we're looking for, oh, and I guess I should say, I didn't really say in the problem description, but I should have said, you know, they start basically from rest, so they didn't get like a running start, so they just kind of edge out over the hill to get going that way, right? So we're looking at, so we want to know what's this distance, right? How far did they travel through the grass? So we can label that here to here, and I'll call that distance d, lowercase d. All right, so how far did they travel through the grass? Oh, and the other thing that we need to, so we'll define our height equal to 0 at the bottom. Height equals 0. So that means that we're starting at a height of 15 meters at the top. H equals 15 meters at the top. Okay, so let's look at our points, right? So we're going to connect point 1 here to point 2 there. And okay, so our system then, and really it probably would have been a good idea for me to write down my definition of the system for the first problem as well. But I'll take my system to be the child and Earth system here. So that means that I'm going to use a potential energy due to gravity in my calculation. Okay, so yeah, so let's go ahead and write down our energies at point 1 and point 2. So the types of energy that we can have here, well, so we really, the previous problem had all of the 3 types of energy that we're working with, right? So we could have kinetic energy, and then we have 2 types of potential energy, gravity and spring potential energy. So in this problem, there aren't any springs. So the only types of the only types of energy that we have possible are going to be potential energy due to gravity and kinetic energy. Right. So I said, just to clarify my statement of the problem, that the child just starts from rest and just, sort of gently eases out onto the descent. So the kinetic energy to start is going to be 0. So the energy at point 1 is going to be just the potential energy due to gravity. So that's mgh. All right, so you'll notice, okay, we have the height given, but we don't have the mass of the child given. So we're expecting, if this is a well-written problem, we're expecting that mass is going to eventually cancel out. Okay, how about the energy at point 2? Right, so potential energy due to gravity, and then plus kinetic energy. Well, let's look at the problem statement. It says that they are coming to a stop. So that means that the kinetic energy is 0, and they're at the bottom of the hill. So the potential energy due to gravity there is 0. So that means that our energy at point 2 is just 0. So here we can see right away that there must be some external work. And as I said, and whenever you see friction, there's going to be external work. We know, and we can also tell that because this is not 0. The energy 1 is not 0, but energy 2 is 0. Right, so they're not always the same. So that we do our next step, which is to say, okay, the external work is going to be equal to the change in total energy, which is equal to E2 minus E1. Right, so I'll go ahead and, well, our external work here is going to be the work done by friction. So I'll go ahead and just write work done by friction is equal to E2, which is 0, minus E1, which is mgh. Okay, so now we need to remember what the definition of work is. Right, so we have in this area here where the where friction is doing work on the sled, the displacement is toward the right, but the force of friction is toward the left. Right, so we know that the work done by friction is always negative because the force of friction always points opposite to the direction of the displacement. So I can say that the work done is going to be negative of the force of friction times the displacement, and that's going to be equal to negative mgh. Right, so now I have a negative on both sides, so I can cancel that out just so I don't have to keep copying that down. So the force of friction, if we remember, let me, oops, I keep forgetting I don't have to go there. The force of friction is equal to mu, the coefficient of friction, times the normal force. Right, and in this problem, if we could draw a quick free body diagram, we're going to have normal force pointing up, the force of gravity, you can write mg, pointing down, and then the force of friction pointing left. Right, so there is an unbalanced force, right, which is going to cause an acceleration, slowing us down. But what I'm really looking at here is in the vertical direction, we have the normal force and the force of gravity are the only things in the vertical direction, so we know they have to balance out. So, if you want to be thorough, you should write down, well, F net in the vertical direction is normal force minus gravity. There's no acceleration in that direction, so they equal 0. Or we can just we've done this enough that we can hopefully cut to the chase and say that the normal force here just balances out the force of gravity, so it's going to be equal to mg. Right, so I can take that and insert it down here, which gives me mu mg is the force of friction. Okay, so bringing that back over here. Now, one thing to note here is we can't actually calculate a value for the force of friction, right? Because we know mu, we know g, but we don't know the mass. So we have to do this one algebraically. So we have to bring that over here and say, okay, force of friction is equal to mu mg times displacement, and then we have the displacement there. So that's going to be the work done by friction, and that's equal to mgh. Right, so that's just copying down this equation here, but replacing the force of friction with mu times mg, and canceling out the minus signs because there's a minus sign on both sides. Okay, so now we see what we hoped and what I knew would happen is that the mass cancels out. So I'll just cross that out on both sides. And then we're trying to find the displacement, how far the child is able to sled through the grass. So I'm trying to solve for d, so that means I should divide by mu times g on both sides. Oops. Mu, that's a terrible mu. Mu times g there, and then mu times g there. Now I can also notice, well, I'll save that observation for just a second here. So let's copy that down. So that means I get displacement is going to be equal to, okay, somebody already noticed, why doesn't g cancel? I could have just done that initially and said, so Jaden, thank you. Yeah, so I could have just said, well, let's look at common terms on both sides. I didn't quite have that foresight, so let me just copy down what I've written. I've got g times h divided by mu times g, and there we go. Now, if you didn't notice, I mean, that's fine because we know what g is, so if you had just plugged in numbers, you'd be fine. But that's going to save us some calculation. So that's going to give us h divided by mu. Okay, so our height was 15 meters, and mu is a number 0.20. So dividing by 0.2 is like multiplying by 5. So that would give me 75 meters. Okay, so in this problem, we had a situation where the energy was not conserved, right? So there was external work done by friction. And so whatever energy that we had to start, that was all taken away by friction. And so, in the end, what we're looking for is how far the child went through the grass, but we're using that work as a change in energy to calculate that. So we, as I said, probably most of you are going to want to define your system as broadly as possible. The other option that you could have done is just define the child as the system, right? In that case, gravity would be doing positive work, and then friction does negative work. In the end, you would end up with the same calculation and the same displacement. So any questions on that problem? Okay, so those were the examples that I wanted to go through today. So what I want to do now is we can do sort of office hours at this point, because this would be a normal time for office hours. So if anybody has questions, we still, as a reminder, there's the expert TA homework. I forgot to send out an additional reminder, so it's supposed to be due this evening. I will give an extension on that until Friday. But if anybody has worked on that and has questions, we can, you can hang out now and ask questions about that homework or anything else that you would want to talk about. So I will, at this point, I'll stop sharing this. I'm going to stop the recording of the class.